Okay, I'm having all kinds of technical difficulties today. Yeah, I already made a video talking about this stuff, but then the video got deleted. So I'm just going to show you this again and talk about it again. But it's all already written. So 4.2 is about Rolle's theorem and mean value theorem. Rolle's theorem says the following. If you have a continuous function that's differentiable, and there's some technicalities here, like it has to be continuous on the closed interval, so it has to be continuous at A and at B. It only has to be differentiable in between. It doesn't actually have to be differentiable at A or at B. It does have to be continuous there, though. And f of A equals f of B, then there exists some c in the open interval where the derivative at c is 0. So I have an illustration here. This is a graph. I drew it so that f of a and f of b are the same, right? This is the same y coordinate, f of a and f of b. And it's a continuous differentiable function. And all this is saying is that there's some c in between where the derivative is 0. That means there's a horizontal tangent line. So here's one possible value of c. Here's another possible value of c, because there's a horizontal tangent line here and here. Rolle's theorem just guarantees that this happens at least one point. It could happen at 2 or even more than 2. Mean value theorem has the same two conditions, or the same, like, it has to be continuous and differentiable. Continuous on the closed interval, differentiable at the open interval. So if we have those two things, then there is some value of c such that the derivative equals this. So what is this? This you might recognize as the slope of the secant line. So this is saying that the slope of the tangent line at C equals the slope of the secant line from A to B. So here's an illustration. Here's a graph. Remember, we're no longer assuming that f of A and f of B are the same. So this point and this point are not the same y-coordinate, obviously. But here's the secant line, and all this is saying is that there's a value c where the slope of the tangent line equals the slope of the secant line, meaning that the tangent line is parallel to the secant line. So once again, here's the secant line, and I found here's one point. This could be a value of c, like this x-coordinate could be c, because the slope of this tangent line, it really looks like this is parallel to the secant line. By the way, there's another value of c over here, because this tangent line is parallel to the secant line. The mean value theorem just guarantees one value of c. There might be more than one, like in this case there were 2. Sometimes there's even more than 2. And by the way, Rolle's theorem is just a special case of the mean value theorem, because if you notice, if A and B do happen to have the same y-coordinate, like they do in Rolle's theorem, if I draw the secant line is just horizontal because it has the same y-coordinate. And what Rolle's theorem is saying is that there's a tangent line that's also horizontal. So Rolle's theorem is basically just the mean value theorem when you're talking about horizontal lines. The mean value theorem is when you're talking about lines that could have any slope. So this section is not terribly hard. It's most of the homework is just about verifying the conclusion of Rolle's theorem or mean value theorem, or checking the hypotheses, etc. So we have a specific function and a specific interval, and we are supposed to verify that the function satisfies the hypotheses of Rolle's theorem. And we're supposed to find any numbers C that are guaranteed by the theorem. So real quick, what are hypotheses? A theorem has hypotheses and a conclusion. The hypotheses are the assumptions. Hypotheses typically follow the word if. So if this is a hypothesis, this is a hypothesis, and this is a hypothesis. The conclusion typically follows the word then. So the conclusion is that there exists some value of C such that f prime of C equals 0. So there are three hypotheses to Rolle's theorem. It's number 1, number 2, and this one that we didn't give a number. So let's check those. The function is supposed to be continuous on the closed interval. It is. It has to be. We're supposed to check that it is. We should put some kind of reasoning. We shouldn't just put a check mark. I wrote the following reasoning. It's a polynomial. This function is indeed a polynomial. Polynomials are continuous everywhere. In particular, it's continuous on this interval. But it's easy to say because it's continuous everywhere. Hypothesis number 2 is that it's differentiable. The easiest way to show that it's differentiable is just take the derivative. The derivative is this. The derivative is also a polynomial, and that exists everywhere. The domain is everything. So it's differentiable everywhere. In particular, it's differentiable on this interval. I guess it only has to be differentiable on the open interval from 0 to 3. But it's easy enough because this is differentiable everywhere. So that's the second hypothesis. The third hypothesis is the one that we didn't assign a number to. It's just the statement that f of a equals f of b. So I just check that. A and b are 0 and 3. I put them in. F of 0 is 1. Sure enough, f of 3 is also 1. So that checks out. So we checked all three hypotheses. Now the last thing we have to do is to find any numbers C guaranteed by the theorem. What does that mean? The theorem guarantees a value C such that f prime of C equals 0. That's what it says here. So luckily I already took the first derivative. It's this. So f prime of C would be 2C minus 3. I set that equal to 0, and I solve it for C. Once again, the theorem guarantees the existence of at least one C. So it's possible that I would find more than one solution, and I was supposed to find all of them. Remember, this has possibly multiple numbers C that I could find. This just has one solution. You may run into problems where you have more than one solution, and that's fine. Just list them all. Okay. For the next problem, we're basically doing the same thing, except it's mean value theorem instead of Rolle's theorem. Find any number C that satisfy the conclusion for this function on this interval. Notice the instructions don't actually say to check the hypotheses. I'll go ahead and I'll check the hypotheses out loud just because I think it's good practice. But the instructions formally don't actually say to check the hypotheses. But let's do it anyway. For the mean value theorem, you just check 1 and 2. There's no more requirement that f of a equals f of b for the mean value theorem. The hypotheses are just 1 and 2. So I just have to check that it's continuous on the closed interval and differentiable on the open interval. This function, it's 1 over x. It is this is an elementary function. It's not a polynomial, but I could say that the denominator is a polynomial. This makes it an elementary function. Elementary functions are all continuous on their domain. This one does have a possible domain restriction at x equals 0, but that's not in the interval. So the interval only includes numbers where this is it's in the domain, and so it's continuous there because it's an elementary function. It is also differentiable, because that's the second hypothesis. The derivative would be this, and again, this is defined everywhere except x equals 0, which again is not in the interval. So everywhere in the interval, it's differentiable. And again, I guess it just needs to be in the open interval from 1 to 3, but that doesn't matter because the only problem we would ever have is at x equals 0, and that's, we're staying far away from x equals 0. Okay, so the hypotheses check out. Let's find the number c. So what the mean value theorem says is that f prime of c should be this, right? It's like this. F prime of c is f of a minus f of b over b minus a. So let's find this number. So f of 3 minus f of 1 over 3 minus 1. So I plug that in. For my function, it's 1 over x, so it's 1/3 minus 1 over 1 over 2, which is negative 2/3 over 2, which is negative 1/3. So that's what this is. The mean value theorem tells me that there should be a value c such that f prime of c equals that. So I'm going to take f prime of c. I already found f prime of x, so I can just put a c in there. And I'm going to set it equal to that number that I got from there. I solve this for c. So I can cancel the negatives, and I can do the reciprocal of both sides. So I just get that c squared equals 3, like this. I can do the square root, so c would be plus or minus root 3. This would be an example where maybe right now it looks like we found two values of c, and that's possible, but we should be careful. The mean value theorem guarantees that there's one value for c, or at least one. Sometimes you will find two, but in this case, what we have to check is that these are actually in the interval in question. The interval in question is from 1 to 3. Negative root 3 would be a negative number, so that wouldn't be in here. Positive root 3, by the way, because root 3 is about 1.7, positive root 3 would be in here. So for my final answer, I'm just going to list the positive root. It is possible to have more than one answer, but you should check that all the answers that you get are actually in the interval and only keep the ones that are in the interval. So in this case, we got back down to one answer again.